Hi guys, in this video we continue talking about the Sturm Liouville theorem, and we are going to state the Sturm Liouville Eigenvalue theorem. So this is going to be the Sturm Sturm Liouville Eigenvalue theorem. So the regular Sturm Liouville eigenvalue problem consists of the Sturm Liouville differential equation. So let's consider the Sturm Liouville. Just let me call it SL, okay? Sturm Liouville differential equation. And this equation looks as follows. So derivative with respect to x, p of x times the phi dx plus q of x phi plus lambda sigma x q phi, phi equals to 0. And x is between a and b, okay? And this is a differential equation, so don't panic. For our case, p was constant, p was 1. So if p is 1 times the phi dx, pues you got second derivative with respect to x, right? So our phi was capital X, x of x, okay? Phi was capital X of x, okay? So so it looks like that. So that's why I say this is the simplest case. And then we have q was 1. No, probably better to say this q was 0 in our case. Lambda was lambda, and sigma was 1. Okay? So if you do that, we will obtain the case we solved in our previous video. Okay? That's the first part of the equation. But that's not it. So this is the differential equation. So there are many cases. Because p could be changing on space, and q, so this has variable coefficients. So you learn in undergraduate, or at least I tell my students in undergraduate, the differential equations we solve as undergraduate students are constant coefficients. So here is variable coefficients. So welcome to graduate school. Okay, so this is subject. This equation must be solved subject to the boundary conditions, it looks like this. Okay, so b1 phi of a plus is not b1, well, you can call it b1, b2 the phi dx evaluated at a equals 0. So remember, a is the value, right? So you are in the interval a and b. The differential equations is on the open interval, but you need the values here on the corners. So, and the other is beta 3 phi of b plus beta 4 the phi dx of b equals 0. So again, don't panic. For our case, beta 2 and beta 4 were 0, right? Because I don't have these guys. I don't have those derivatives. and B1, B3 were 1. So I had phi of 0 equals 0 and phi of L equals 0. So in my case, this A was 0 and B was L, right? So I'm here. So 0 L, so I don't have the other ones, but I could, so that's why I'm saying this theorem is so important, because it's so general, okay? So again, I'm writing this so big. Okay, so I don't have to do so much editing later. I'll try to decrease it. Okay, so that's my Sturm Liouville theorem. My Sturm Liouville theorem, my Sturm Liouville problem. Okay, so my Sturm Liouville problem, let me erase all this, is this differential equation subject to these initial conditions. So the possibilities are as many as you want. It's really extraordinary. Okay, so let's go to the statement of the theorem. So statement of the theorem. So statement of Sturm Liouville theorem. So what it says is that so the statement of the Sturm Liouville theorem. So it says many things. So first thing it says that all the eigenvalues lambda are real. All the eigenvalues lambda are real. Okay. So first of all, we notice important observation here is to observe that this problem is indeed a linear algebra problem, because as we already said, we are finding eigenvalues and eigenfunctions. Okay, so it's saying all your eigenvalues are real. Why is this good? Or why is this important? So if you have done some physics, you know that the eigenvalue, well, maybe probably better quantum mechanics. In quantum mechanics, the observables, or no, even classical mechanics, the observables, what is the observables? What you see experimentally are the eigenvalues. And the eigenvalues make sense to be real. If they are complex, and now we need theories, well, the eigenvalues can be complex. But traditionally, the eigenvalues are real to have a significant meaning. For example, you solve the Schrödinger equation, the partial differential equation, or the Schrödinger equation. Actually, if you go to the the Schrödinger tomb, so let me see, let me show you here. Let me show you here in Google how the Schrödinger equation looks like. Okay, so Schrödinger equation. If you go to the tomb, and so this tomb is in Germany. Okay, here. So this is one version. This is a partial differential equation, but really there is on the tomb of Schrödinger is this one. Look at this one. So this is basically an eigenvalue, eigenfunction, sorry. This is the operator, and that is related like that. However, there is another famous one. Like this is the one. That one is the one. So it's saying this is the eigenvalue. This is the eigenfunction. You see energy eigenvalue. And the Hamiltonian operator is just an operator that instead of being a matrix is an infinite matrix. And we call it energy operator. But that's what is in the tomb of Schrödinger. So let me see Schrödinger equation. No, Schrödinger Tom. I know because my advisor sent me a picture. He was visiting Schrödinger Tom, and he was sending me a picture, but I don't see the no. Well, I guess it's. Oh, but I noticed that we have the same name, Erwin Schrödinger, and me. We have the same name. Okay, so I don't see the. Well, I guess this is very valuable. What the picture of my advisor sent me. I don't. I don't see. The top. Okay. Anyway, I don't want to make this video long. So that's the first statement of Schrödinger equation. So my point here is the the Schrödinger equation is already here. Not is more general. Yeah, it's more general, but it could be presented like a Sturm Liouville problem when it's very general. It's basically the same idea. The linear operator times an eigenfunction equals an eigenvalue times the eigenfunction. Okay, so I think it's that's already very interesting. I think. Part 2. It says that there exists an infinite number of eigenvalues. There exists an infinite number of eigenvalues, and even better, you can organize it in order: lambda 1, lambda 2, lambda 3, lambda 4, and so on. Okay. Part 3. It says that corresponding to each eigenvalue there is an eigenfunction. So corresponding to each eigenvalue is a lambda n, there is an eigenfunction. There is an eigenfunction denoted, in this case we denoted phi sub n of x, because our equation here we didn't put x, we put phi. Okay, so we just call it phi sub n of x, which is unique within arbitrary multiplicative constant. So which is unique up to over 2, which is unique to, I like it better like they say, to within to within an arbitrary multiplicative constant. An arbitrary multiplicative constant. Okay, so that's what I was choosing here. I was getting plus or minus, but I said let's just choose plus, because plus or minus does the same eigenfunction. Okay, for that, you know, something really interesting here. Let me put it here. It looks like right now it's not gonna be, maybe you're not gonna have many sense of this, but phi sub n of x has exactly n minus 1 zeros. Has exactly n minus 1 zeros for x between a and b. Well, actually this is very nice. So what are they saying? They're saying I'm making my function between 0 and L, right? So my first function is sine n pi x, right? So is if n equals 0, so it don't have anything interesting. If n equals 1, so I have sine pi x over L. So that means this is 1, so this function goes like this. So that means I have no zeros, because it has, for the first one, 1 minus 1, I have 0, 0, so I don't have x intersection. So that should be my first one, right? Because n is 1, so it's sine of pi x, right, over L. So my next one, this is my first eigenfunction, let's call it phi1. My next one is gonna have 2 zeros. And sorry, is phi2, so has n minus 1 0, so it has 1 0. So it's gonna go, it has 1 0 between 0 and L, okay? 0 and L. Because it looks like I have zeros here, yeah, but that I'm saying between 0 and L. This is phi2. Then the next one I'm gonna have 2 zeros, so 1, 2. So my next one is gonna look like this. That's phi3, and so on. So you see, that's your basis. So it's very, even tells you the zeros. It's amazing. This theorem is amazing. The next one is statement 4. It says the eigenfunctions for a complete set, meaning that any piecewise function f of x can be represented by a generalized Fourier series of the eigenfunctions. Furthermore, this infinite series converges to the sum of the difference, sum of the left and right hand limits divided by 2. Okay, so let's put it. So what are we saying here is that f of x is gonna be the sum of n equals 1 to infinity of an phi n of x. So if I choose an f of x special, so this is what it's saying. The eigenfunctions phi n of x so this set form a complete set. So it means meaning that any continuous function, we prove this. Okay, we prove this. Remember, but more than that, meaning that any piecewise smooth function. So that means this f of x could be continuous between 0 and L, could be continuous. Well, sorry, this is not a function. It could be continuous, or could be this is C, let's say this is 0, this is L, could be piecewise continuous. So f could be this one, or f could be this one, continuous or piecewise continuous. Then I can express these functions as an infinite sum of phi sub n of x times a sub n when we know already what are the a sub n, because remember we worked that out long time ago. So those are the integrals and the phi sub n of x. So as long, because they're gonna be orthogonal, okay? So we can deduce what is a sub n. So as long as f of x is a piecewise function, they can be expressed in this form. And the other thing I want to say, piecewise function f of x can be represented, and look at the term we're going to use, can be represented by a generalized Fourier series. I like this term. It's a generalized Fourier series because we know Fourier series. We are experts now in Fourier series, right? But we basically just know sine, cosine, and full Fourier series. But this theorem is saying more. There is much more than only those three. There are generalized Fourier series that are be connected to differential equations. So basically, whatever p, you choose a p, you choose a q, you choose a sigma, that will generate you a new generalized Fourier series. Okay, so you will see that the examples we're gonna have are basic when p's, q, and sigma are constant. Okay, but they can be much more general, and I will make you a list. So I sold you this idea. Okay, is by a generalized Fourier series of the eigenfunctions. So basically, my eigenfunctions, my phi sub n, are gonna be the base for the Fourier series, for the generalized Fourier series. Okay. So furthermore, and we prove this. Furthermore, this infinite series converges to fx plus fx minus divided by 2. This is, so in general, see, if the function is continuous, the function converges here. If the function is continuous, converges here. If the function is discontinuous at this point, the function converges to the middle. Remember, that was the part 2 of the proof. So we proved for this point, we proved this for this point, we didn't prove for the middle point. We could, but you know, I'm not sure how much to give you. I was afraid to you will be too tired of seeing this proof, so I leave it like that. So finally, remember, you spend a lot of time proving in this homework proving orthogonal stuff. So eigenfunctions belonging to different eigenvalues are orthogonal relative to the wave sigma x, to the wave function sigma x. So this is function sigma x. So this is not a problem for us because sigma x for us is 1 for us. In other words, the following integral is 0. The integral between a and b of phi sub n of x times phi sub n of x times sigma of x dx equals 0 if lambda n is different of lambda m. So you prove that, right? Sine of nx times sine of mx, the integral between, I don't remember, 0L or 0 pi, I don't remember. Sigma was 1, that gives you 0. So this all is by free thanks to this Sturm Liouville theorem. So that's why engineers and physicists, they don't have to work so hard, because this theorem gives them everything. They just have to solve the equation. If they can solve this equation, they will find the whole, all this by free. Okay. So that's the Sturm Liouville theorem. And let me see how much time I have in this video. 25. I guess I can list. Well, I'll list the main cases of the Sturm Liouville theorem in another video. So just to make sure this one doesn't get broken or something.